Hello everyone, I come back with part 3 of 7 of week 3 Introduction to Adaptive Control. Okay, you see.
The purpose of this lesson is to learn the concepts of trajectory control and force control. We will see why they are important in manufacturing industry using illustrative examples. We will also introduce the concept of adaptive control approach to enable process control. Computer numerical control, or CNC machines, lathes, and robots are some of the common machines used widely in manufacturing industry. Most of the times, these machines are performing repetitive tasks over and over again without any break. Normally, machines or robots are programmed to follow very precise motion paths. A class of simple tasks may need only trajectory control, where the robot end effector is moved merely along a prescribed time trajectory. In many manufacturing applications, following the exact trajectory is enough for tasks at hand. The examples where precise motion control is important includes robots performing pick and place tasks, robots spray painting car parts, or lathe cutting through cross-section of a circular workpiece into an ellipse. However, in a number of complex manufacturing tasks, such as assembly of parts, manipulation of tools, and robotic polishing requires control of physical interactions and mechanical contacts. In other words, some complex tasks require precise force control and necessitates the robot or the end effector of the machine react to the force acting on the end effector and adapt its motion to uncertainties of the forces involved in the task. Let us now try to understand the concept of adaptive process control in manufacturing setting. The industrial nature of manufacturing shop floor causes variation in environmental factors such as temperature, humidity, fluctuation in material quality, and human factors. Multiple such factors can affect the quality of component fabrication. A control system in which the controller adapts with varying and uncertain parameters can protect a system from unwanted errors. The concept of adaptive process control, or in short APC, accounts for variation in the external environmental factor and is very useful in manufacturing processes. Let us consider a simple example of cruise controls of cars to understand the basic concept behind the adaptive process control. Cruise control systems automatically control the supply of fuel to the engine so that the vehicle does not drop below or exceed a speed selected by the driver, even when the external environment in which the car is operating is changing. The external environment factors in cruise control example could be changing road conditions, such as change in slope and change in wind speed. The speed of the vehicle remains constant even if the outside conditions change. A fixed control method, in this case, enabled by constant supply of same amount of fuel, may not be efficient enough to deal with fast-changing situations. The supply of fuel has to change and adapt as the external conditions fluctuate. In manufacturing industry, the concept of APC is widely used to implement many practical solutions. For example, APC of injection molding process accounts for variation in external factors such as material quality, humidity, temperature to enable faster injection molding that produces very high quality parts at a rapid pace. Adaptive control is enabled by two main components. One, sensors. Sensors are used to acquire information about input and output of the processes such as speed, acceleration, humidity, and temperature. The sensors provide the change in process parameters by calculating the difference between input and the output of the process. Component 2 is enabling the change in the system process parameters to account for the variation that is happening in the process.
Okay. It shows. Apply and apply. Docker sensor used in automatic assembly. Okay. With the help of following video, what makes the robot move? What makes the robot move? So I don't need this one. What makes the robot move?
Robotware Assembly Force Control from ABB and ATI Industrial Automation. Is a new robot option that will greatly facilitate the use of robots for assembly tasks. Assembly FC adds sensor feedback to allow the robot to search for the correct assembly position. Movement of the robot is force-controlled. Forces and torques are
robot is force control.
measured by the sensor at the wrist of the robot. A measured force makes the robot react with a movement in the sensed direction, which acts to reduce the contact force.
Camshaft.
This part of the video shows a camshaft inserted into a diesel engine block. The programming was not done to be time optimal, but rather to demonstrate the concept of force-controlled assembly. You can see that the robot is compliant, and with the help of a circular search pattern and an oscillating force, the camshaft will find its way in.
Camshaft insertion.
In this part of the video, a half shaft with a complex spline coupling needs to fit in the differential gearbox. The half shaft connects the differential gear with the wheel on a car. This part of the video shows the fitting of a piston into the cylinder of an engine block. The tolerance
Why run so low? Slowly.
are tight, some hundredths of a millimeter, and until now, assembly has always been done manually or done by a specialized machine.
Done by specialized machine to compression assembly.
Here we see the assembly of a torque converter. The torque converter has several steps of spline fitting.
How control this assembly.
The video shows the possibility of combining different search strategies when the complete assembly contains 4 completely different steps. Assembly force
Conversion very slow motion.
control can be used for product testing, not only assembly operations. Typical examples are car seat tests or testing of furniture. In this case, the robot simulates the opening and closing of a glove compartment. The forces are very consistent. There is no overloading, providing reliable testing results. Here, the force-controlled robot applies forces and torques to a steering wheel, simulating a driver getting into or out of a car. With robotware assembly force control, it's now possible to automate assembly tasks which earlier required skilled personnel.
Okay. So, what am I doing? Oh. Control. Maybe. Yes, for control. The movement of the robot shown in the video is for controlled sensor at the wrist of the robot measure force and torque. A measure force makes the robot react with a movement in the same direction, which acts to reduce contact force. Okay. Number 4. Commercially. Okay.
Commercially.
Commercially available software. Okay, commercially available software.
This lesson will introduce commonly used commercial software systems for manufacturing process control. As you see now, at a local company in Western New York, Polymer Conversion Inc., sensors mounted on a manufacturing machine is providing real-time manufacturing process data. The streaming data could be used to enable real-time statistical process control, or SPC. On this displayed chart, you can see in blue lines are upper and lower specification limit of the process, and on the left-hand side, you see the overall process histogram. Such real-time streaming of data could be used by plant supervisors to enable greater quality control of manufacturing processes on the shop floor. In addition, you also see that data coming from various machines could be used to schedule several different jobs on different machines to optimize the overall resource allocation. Real-time job allocation could be enabled through intelligent machining paradigm. Next, you will see a link to an example of highly automated factory using intelligent machining paradigm to manufacture technically advanced liquid sprayers or liquid dispensing systems.
Okay.
Having seen the use of software for manufacturing process control, we'll outline 3 commonly used softwares. WinSPC. WinSPC is a commonly used software application to achieve reliable process control. WinSPC allows for real-time statistical process control and enables process optimization. These capabilities allow for process monitoring, implementation, and compliance report generation. Rensa software. Rensa software assists in achieving intelligent process control technologies in traditional manufacturing processes and leads to better quality assurance and higher benefits and yields. OpenCNC, which is an open source software that has an architecture that enables the manufacturers to integrate additional off-the-shelf software and hardware to its existing components, such as precision drills, routers, and grinders. Some good features of this software platform is easy upgradability by the user, easy interface with personal computers or PCs, and cost saving throughout the product life cycle.
Okay. Okay. WinSPC initial open CNC. Okay. So we insert something here. Closing this one, state the need for adaptive control. After viewing the following video, state at least one unknown changing input. After viewing the following video, what's the parameter measured by adaptive controller? With the following working of adaptive control select on. State the need for adaptive control. Research adaptive. No. Okay. State the need for adaptive control. So put something to increase productivity, quality, and quantity. That's it. At least one unknown changing input.
T-minus 90 seconds and counting. All systems are go. We're about 90 seconds into launch of Space Shuttle Discovery.
Unknown input.
T-minus 60 seconds and counting.
Counting.
We are transferring to orbiter internal power at this time. Discovery is now running off its 3 onboard fuel cells. Coming up on a go for auto sequence start. And we have a go for auto sequence start. Discovery's onboard computers have primary control of all the vehicle's critical functions. T-minus 17 seconds and counting. 15, 12, 11, 10, 10, 9, 8, 7, 6, start, 2, 1, boost ignition, and liftoff of the Space Shuttle Discovery, returning to the site station, paving the way for future missions beyond. Separation confirmed. Guidance now converging. Discovery's onboard computers commanding the main engine nozzles to swivel, aiming the shuttle for its precise target in space for main engine cutoff.
Discovery, Houston, negative return. Negative return.
Okay. Window changing code. Win. Speed. Okay. Let's see. At the very following, what is the parameter control by adaptive control? Okay.
This
Adaptive
project explores
control
using
for
adaptive control for
damage.
damaged quadrotors.
Cable.
Quadrotors are naturally unstable systems, but modern control techniques, such as LQR, pole placement, or MCP, are able to stabilize and control them very effectively. These techniques require an accurate model of the physical system in order to be effective. So what happens when that system changes? One of the most common changes is bending or breaking propellers during a crash. Even a small change in propeller geometry can have a large impact on the relationship between rotational speed and thrust, quickly changing the system away from the model and breaking our controller.
Breaking our controller.
In this flight, we simulate damage by cutting 15% of power to one propeller of the drone. As you will see, the drone becomes unstable and crashes. In order to fix this, we design an adaptive LQR controller, which learns offsets from the commanded thrust and torque to make our expected acceleration match our measured acceleration. Our measured acceleration is multiplied by the inertia matrix of the drone and then compared to the commanded torques. The resulting error is then multiplied by learning rate gamma and integrated. Discrepancy between the model and the physical system generates these torque offsets, which are used to correct the output of our model system. In simulation, we compare the standard LQR controller on the left to our adaptive controller on the right. Position is on the top and orientation is on the bottom. A propeller failure is simulated at 10 seconds. Notice that the standard controller ends with serious steady-state error, while the adaptive controller quickly returns to its correct values. So, let's try it out. As you will see, the drone moves slightly to the side when the error is introduced, but it quickly returns to its reference position. These graphs compare the two flights. The standard controller is on the left, and the adaptive controller is on the right. Positions on the top and orientations on the bottom.
Okay. So, parameter measure. You can see the picture, and you can see here. Yeah, yes.
It's these torque offsets.
Store, measure, acceleration. server which of the following are working operating control? Primarily use sensor to archive information input and output from the process. Primary use sensor. Get system process changing mechanical input output. Get system changing modify no system modify control method. Modify control method with new information system. Parameter. Modify no system parameter. Yes, we can modify parameter control methods. No. Yes, system changing. Yes. Correct. So it all. Okay, the control virtual access from command push and talk to my person. Smaller to virtual offset from command push and talk. Okay, wind, gravity, speed, yes. Consider the situation that we don't know the process completely or the process will change in time, yes. A solid fit control method may not be efficient enough to deal with fast-changing situation. Is with information, yes. Yes. Consider a situation that we don't know the process completely or will change in time. Okay. What? We will combine this one. Yes. When we don't know the process completely, okay. When observe this. Okay. So all of them. Okay. Talk. Okay. So now, yeah. Industry robot. How to manage trouble from start and won't require any human intervention. Intentional automatic trouble from start and won't require any human intervention. For maybe you need to processors can stay within control over time without intervention. From a tactical process control system can obtain feedback from only single interpoint. Which of the following function can be performed by rolling control? Interrogation process. Execute changing one. Okay. No, it can execute. Analytic control method can include share with new operation users with to conduct server execute action in an accurate manner mean that it executes the change without delay. Accurate. It have delay. Only will have delay. But the following is one input, output, power supply, processor, yes. Battery. The company is manufacturer shape of two different than GMS 50 in and 60 in. Total number of employees work in the company are 11 and can review 1,200 sets per day. Cost for making a single copy file cell by constantly the efficiency of process. What are the information in the process? Input constantly the efficiency of the process is also be monitored. Input the input number of employees should efficiency per day can be geometer of the shut. Okay. Company is manufacturer through the computer. Okay, understand. What are geopost? Geopost input shape. What is the history that can be viewed and the feedback to improve initial process? Improve initial process. Improve initial process. Okay, if you can do Chairman. Yes. And T. Okay, we have something wrong here. 4, yes, one more before. Okay, so we can here. Import 2001. Yes, import course here. Output per day output. Okay. Efficiency will set the review. Efficiency will set the review at feedback. Efficiency. Okay. Okay. We do it again. Fold. 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 No, it's good. Adaptive control method can automatically improve itself with new information. The 2, 4. Okay, efficiency. The efficiency. Okay. 1, 2, 2 shape per day. Okay. Employ 8 and okay. Okay. So okay. What the hell? So 5, okay. 60, 100, 1, 3, okay, yeah, this one correct, but we make something wrong. Count this one. Execute, so okay, we do it again. Okay, this one. Okay. Shit. Okay. The efficiency. Okay. On. Go. To. On. 4. 100. Yes, that's it. Save control software. Machine learning algorithm adaptability. Okay, then we fall.